Good day class, welcome to lecture number 6. If you remember from the previous lecture, we started to talk about contrast enhancement. And we have seen several mathematical functions which we are using in order to do the contrast enhancement. Now today we will continue our talk on contrast enhancement and we will use the histogram processing in order to enhance the contrast of an image. If you remember the definition of the histogram from the statistics or from the previous lecture, we said that histogram will tell us at one specific gray level how many pixels we have in an image. Now, if we calculate the histogram of an image and if we divide the histogram by the total number of pixels that we have an image, we will get something which is called normalized histogram. Now, in a normalized histogram, each value is between 0 and 1 and the summation of all the values will be 1. And it means that what we have a series of the probability values. And the function is now called the probability distribution function. So by dividing the histogram by the total number of pixels, we get the PDF of the image. Now let's see how we can use this histogram in order to enhance the illumination and contrast of an image. We are using a technique which is called histogram equalization. It is a method which increases the dynamic range of gray level in a low contrast image to cover the full range of the gray level. Imagine that you have an image whose gray levels are, let's say, between 35 and 160. As you can see, it's not the full range. After applying the histogram equalization, we will make sure, we will guarantee that we will have this pixel value 0, we will have the pixel value 255. Now, in order to achieve histogram equalization, we will use a transfer function which is cumulative distribution function of a given PDF of gray level in an image. So we will calculate the CDF, cumulative distribution function of PDF, and we will use it in order to do the enhancement, the histogram equalization. And in this slide you see that the new intensity value of the pixel X is calculated by the given formula. In this formula, CDF of X means the cumulative distribution function at the pixel value X. Mean CDF means the minimum value of the CDF. L is the gray level. If for instance we are using the 8-bit representation, L will be 2 to power L, and 8, which is N minus 1 is 255. Our round function guarantees that the result of this calculation is an integer. We know that the pixel values in an image are integer and they are basically unsigned integer. Now, in here, the CDF that we use is CDF of PDF. In some books, some notations, they are using the CDF of histogram. If you are using the CDF of the histogram, this formula that we have in this slide needs to be updated. In the denominator we have 1. This 1 should be updated to the total number of pixels if we are using the CDF of histogram. If the size of the image is m by n, then m multiplied by n is the total number of pixels that we have in the image. So if you are using the CDF of histogram, this formula will be updated in the form that the denominator will be m by n minus minimum of CDF. Now, in histogram equalization, the probability function of the output level is uniform. So what histogram equalization tries to do is, you have a distribution for your image, low contrast, high contrast. We try to convert it into a uniform distribution. And transfer function is simply the CDF. Now, there are a few things that you have to know. We said we are converting into a uniform distribution. What is the CDF of uniform distribution? The CDF of uniform distribution is identity transform. So CDF of uniform distribution is identity transform, and histogram equalization is using the CDF in order to do the transformation. So it means that If you apply the histogram equalization more than once, nothing will be changed. Because after the first conversion transformation, we will get the identity CDF. So afterwards, all the time we are using the identity, so it means that nothing will be changed. So the first iteration of histogram equalization will give the same output as if you apply it 100 or 1,000 times. So this is a very important thing that you have to note. Here in these slides, we see the low contrast picture of Obelix, and we see the output of the histogram equalization. We see how the histograms are being changed. In these slides, we see a face image from Caltech Space Database and its histogram. And we see that the output of the histogram equalization and its respective histogram, how the histograms are being changed. Note that histogram equalization is a very simple method. Lots of people are using it or using it in order to do some comparison with their own method. But as you can see, it destroys the nature of the histogram of an image. And in the case of color image, it caused some artifacts, some artificial colors, which are not very good. So we need to have some other techniques which take over of these problems. We have local histogram equalization, dynamic histogram equalization, which are taking care of these problems. Another method which very new and takes care of all these problems is a method called singular value equalization, proposed first in 2008. Now, singular value decomposition is used in singular value equalization. SVD is a concept which is known in mathematics, and I'm so sure that you are familiar with that from linear algebra course. We know that any matrix A can be written as a multiplication of two orthogonal square matrices. We call them U and V. And a matrix containing the sorted singular value on its main diagonal, starting from the biggest singular value to the lowest singular value. And as you can see in these slides, so A can be written as U multiplied by sigma multiplied by V prime. So we have to remember that the sigma 1 is much bigger than the other sigmas that we have in a singular value matrix. This means that manipulating this sigma 1, changing this sigma 1 will directly affect on the illumination of the image. So this is the idea behind the singular value equalization. We try to manipulate the sigma 1 in a way that we are enhancing the contrast and illumination that we have. For doing that, we look at the size of the image and we generate a new image of the same size, but this generated image has a very important property. The distribution function of this new generated image will be a Gaussian distribution with mean 0.5 and variance of 1. Then we are calculating a correction coefficient, and this coefficient is generated by calculating the ratio of the maximum singular value of the generated image over the maximum sigma value, singular value of the image. And then we use this correction coefficient in order to calculate the equalized image, the enhanced image. Here, in this slide, you can see a low contrast image, the output of histogram equalization, and the output of singular value equalization. And I think that you can appreciate how singular value equalization overperformed the histogram equalization. Now, today we talked about histogram processing. We defined histogram, normalized histogram, PDF, we talked about CDF. We saw how histogram equalization works. We said that the transfer function is CDF, and we said that the output of the histogram equalization we have a uniform distribution. We talk about what is singular value decomposition and how singular value equalization is working. Now, next time we will continue our talk about image enhancement in the spatial domain, and we will see a few more arithmetic and logical operations that we will use in order to do the image enhancement. I hope that you enjoyed today's lecture. Be seeing you in the next lecture.